Hello, and welcome to the Daily Space for today, Monday, October 19th, 2019. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. Welcome to Monday, people. It is the most Monday of Mondays. This is going to also be a Monday of announcements, so please bear with me for a moment. The news is coming. First off, I'd like to share that we're going to be standardizing our news segments to about 30 minutes. This means more science most days, but, and there's almost always a but, we're also going to be going back to a 4-day week. We're going to be coming to you live Tuesdays through Fridays and bringing you all that is new in space and astronomy for a longer period of time. So overall, you're getting more science just on fewer days of the week. Next, tomorrow we will be hosting a watch party for the OSIRIS-REx mission's asteroid boop. Literally, they are going to be booping an asteroid with their tag instrument as they commit a grab and fly theft of minerals from the asteroid's surface. Join us live at 5 p.m. Eastern, 2 p.m. Pacific on twitch.tv/CosmoQuestX. We'll also have giveaways and rock count reminiscing in the CosmoQuest X Discord server, and we'll be piping the same stream into Discord. Finally, and most importantly of all, I'd like to remind everyone that this October 24th and 25th, we're going to be holding a 36-hour-long hangout-a-thon to raise funds to cover our costs, including the production of this show during the 2021 fiscal year. This is a nonprofit science program, and your donations are tax-deductible where allowed by law. To learn more and donate today, please visit our website, cosmoquest.org. And now finally, to the news. Today's top story brings back our favorite red giant star, Betelgeuse. A new paper published in the Astrophysical Journal with lead author Meredith Joyce looks at Betelgeuse as a pulsating variable star and uses atmospheric physics to bring us new insights on what this red giant is up to. This paper combines new observations that were taken prior to the Great Dimming event last year, but are new in the literature of pulsating variable stars, and combines these observations with new computer models to derive the star's mass and size from its outward behavior in much the same way that one might derive the size of a jug or a bottle based on what notes can be created by blowing across the opening of that jug or bottle. Different sized objects naturally resonate in specific ways. By understanding how Betelgeuse pulsates in what's called the fundamental mode and overtone mode, those are the first two pitches you can make when you blow into a bottle or a jug, these scientists were able to use that physics and work backwards to figure out Betelgeuse's physical size. This let them then figure out more accurately the star's distance, because there's an easy-to-use mathematical relationship between how big something is and how big something appears that gives us the distance to that object. Our current estimates on where Betelgeuse is located use Hipparcos measurements. Hipparcos was a satellite that, prior to Gaia, in fact, more than a decade ago, carefully measured the shift in apparent position of stars in the sky as the Earth travels from one side of the sun to the other. This apparent shift against background objects is the same kind of shift that you can get with your eyeballs if you hold your thumb up to block something and switch which eyeball you're using to view that thing. You'll see your thumb jump back and forth, and in this case, Betelgeuse is the object playing the role of your thumb. Now the thing is, Betelgeuse is a really extended object, and the amount that it appears to jump back and forth against background objects is very small. In fact, Betelgeuse appears to be what is called 42 milli-arcseconds in size. Now, to give you some perspective on this, if you grab a single strand of your hair and pull it out, which I'm not going to do right now, and hold that strand at arm's length, the width of that strand of hair on average for a human being is 1 arcsecond in size. Divide that hair by 1,000, and 45 of those 1,000 pieces put together, that's the size on the sky of Betelgeuse. Now, the amount that Betelgeuse appears to move, that's like 5.95-ish milli-arcseconds. And that ish is there's an error of it could be 0.58 more, it could be 0.85 less. So there's error bars on that measurement from Hipparcos. This is a really hard measurement, and Betelgeuse hasn't been looked at yet with the Gaia spacecraft, which is capable of more accurate measurements. Now, the team on this paper, by working from the theoretical size they got from looking at how Betelgeuse is pulsating in both the fundamental and first overtone modes, they were able to take that physical size that they calculated, look at how big it appears on the sky, and calculate a new distance. And the distance they got was within the error bars of the Hipparcos measurement, but it was at the bottom end of those error bars. And this bottom end of those error bars new measurement is just 530 light years away. Betelgeuse, it turns out, if this paper is right, is significantly closer than we thought. This is 25% of the distance we thought it had before. Now, when it goes supernova, we're still totally safe where we are. It is still plenty far enough away. But this closer distance does make Betelgeuse a bit smaller than we'd thought. If you think something's further away and appears at a given size, it has to be bigger than if it's closer and appears at that exact same size. So we've now shrunk Betelgeuse, moved it closer, but it will still go supernova in 100,000 years. This team's research shows once again that it appears Betelgeuse is still burning helium in its core. It has a lot of evolving to do before it explodes. It looks like this object Betelgeuse started out as a star 20 times the mass of the sun. So we have a while to wait before this smaller than we thought, closer than we thought star goes boom, but it's still going to go boom. It's always cool when completely different techniques can narrow in on more precise values for something. Here we have Hipparcos data and pulsation-based measurements of the size working together to measure the size and getting overlapping error bars, with the truth being, well, where that overlapping error happens to lie. All right, returning to another old friend, we have updates from the Mars InSight mission that the MOLE instrument is finally all the way beneath the surface of Mars. This 16-inch or 40-centimeter long sensor was meant to pile drive itself 3 or more meters beneath the surface of Mars. As it went, it was supposed to being a key word today. It was supposed to measure the temperature profile of Mars soil. I have to admit, more than any other instrument that has gone to Mars in recent years, this was the instrument whose results I was most interested in seeing. The Martian soil both retains heat and protects everything beneath it from the harsh radiation of space. There had been myriad models that indicated that depending on the temperature profile of the soil, it may be possible to have salty liquid water very close to Mars' surface. Now, without actual data, all we can do is model what might be happening based on best guesses and estimates of soil composition, density, and thermal behavior. The InSight mole was going to be our first real measurement of Mars soil at depth. The only problem has been that Mars soil is so different at this location from what was expected that the little probe has been unable to bury itself deep into the surface, or at all into the surface, actually. The cylinder is designed with a pile drive inside that slowly raised up a mechanism within the tube and then sent that mechanism slamming downwards. This motion should cause the mole to bury itself downwards, like a shovel thrust into the ground. Ideally, not reality, friction should keep the mole at the new depth after the weight is slammed down. Then the slow upward motion of the internal mechanism should allow it to just stay put with friction holding the cylinder in place. So you slowly pull up the weight, slam it downwards, friction holds everything in place except when it slams downward and buries itself. This is what was supposed to happen. This is not what actually happened. So they tested this extensively using fake Mars soil here on Earth based on what had been measured by other instruments, by other landers, and it turns out that where InSight landed, they landed in clay. And when InSight's mole tried to bury itself, it just condensed the clay instead of burying itself. Yeah, it's been a problem. To get the mole completely underground, the mission team resorted to using the spacecraft's shovel to push it down. And once the mole was close to the surface, they buried it in dirt and pushed. And now that it's buried in dirt, they're going to continue burying it in dirt until there's enough dirt that they can push on it more with the shovel while it works on trying to bury itself further. It's estimated that it's going to be several months of the shovel piling dirt before they can continue to try and bury themselves downward. At this point, almost 2 years after arriving at Mars, I have to say I am in awe of the continued patience of this mission team. They just keep trying to find new ways to do their science, and my heart goes out to them as they essentially rearrange dirt for the next several months. This is a slow and steady attempt to get science done, and I wish the team all the luck in the world in getting their sensor buried. Strange wishes on a Monday morning, but this is sometimes what is needed to get the science done. Anyways, I have a couple more news notes. Our first news note comes to us from the new Saint X Observatory in Mexico. This new telescope has detected 2 exoplanets orbiting the red dwarf TOI 1266. This demonstrates that this new telescope can do the job it was designed to do. Saint X is an acronym for Search and Characterization of Transiting Exoplanets. And this acronym makes the not intuitive decision to use the I and the N in characterization to make the acronym pronounceable. I think that makes it a backronym, maybe? These test observations were taken just before Mexico's COVID-19 related lockdown began, and the observatory has been closed since then. When the lockdown lifts, this telescope is poised to make planet finding just a little bit easier. While we don't normally cover individual new planet discoveries because they are so common, we will make an exception for this telescope's first new worlds. These 2 worlds orbit their red dwarf home every 11 and 19 days. The inner planet is just 2.5 Earth radii and is classified as a sub-Neptune planet. And the outer planet is 1.5 times the size of Earth, and it counts as a super Earth. These worlds in the new scope are described in a new paper in Astronomy and Astrophysics with first author Bryce Olivier Domery, who says planets between about the radius of TOI 1266 b and c are quite rare, likely because of the effect of strong irradiation from the star, which can erode their atmospheres. SANEX project coordinator and researcher Yelaine Gomez Makeo Chu adds, being able to study two different types of planets in the same system is a great opportunity to better understand how these different sized planets came to be. While Saint X has been chasing new planets, the newly upgraded giant meter wave radio telescope has been chasing gas. Specifically, it has been measuring the hydrogen gas content of galaxies so far away from us that we are seeing them as they appeared 8 billion years ago. According to Aditya Chaudhary, lead author of this study, which appears in the journal Nature, we have for the first time measured the atomic hydrogen gas content of star-forming galaxies about 8 billion years ago, using the upgraded GMRT. Given the intense star formation in these early galaxies, their atomic hydrogen gas would be consumed by star formation in just 1 or 2 billion years. And if the galaxies could not acquire more gas, their star formation activity would decline and finally cease. The observed decline in star formation activity can thus be explained by the exhaustion of atomic hydrogen. This newly published work took advantage of upgrades that took place in 2017. Even with these upgrades, however, their measurements were extremely difficult to make, and instead of just looking at one galaxy at a time to measure its specific hydrogen content, they looked at 8,000 different galaxies and combined their data to get an average measurement. Prior to making the telescope more sensitive, they were unable to measure the weak hydrogen 21 centimeter signal in distant galaxies, even with this stacking technique. Study co-author Jairam Shangari states, the new wideband receivers and electronics allow us to use 10 times more galaxies in the stacking analysis, giving sufficient sensitivity to detect the weak average 21 centimeter signal. We can't wait for the COVID-19 pandemic to be over for many, many different reasons. And wanting to see these two new telescopes do their killer science with this killer new instrumentation, well, those are two of the many, many reasons. When these instruments start producing more science, we'll bring it to you here. Until then, this has been The Daily Space.